Touch the eye, everybody. So just now we have done with the parallel plate capacitor. Alright. So capacitance of a parallel plate capacitor is given by epsilon naught A divided by Q. This is the formula for capacitance. And then capacitance can be defined as charge divided by potential difference. This is what we have defined. This is what we define as charge per unit potential difference. Alright, potential difference between two plates. Okay, so now I have one more diagrams. This is how we charge capacitors. So I will be having a two plate, and we apply a potential difference V. Alright, so the applied potential difference is equal to the potential across two plates. So this is what I have here. Potential across these two plates is going to be, potential across this plate is going to be V, alright, which is equal to potential we apply. And electric field inside place is going to be V divided by distance. So this is what I have. This is how charging of a capacitor takes place. If we don't charge capacitor, then there won't be any electric field inside capacitor, right? So unless you apply electric fields, you apply a potential difference, only then you get electric field. And this is how electric field is. Now if I remove this, potential, still then electric field is maintained, or electric field remain inside these two plates. And the potential difference is also maintained across this. Why? Because it is dielectric or it is vacuum, whatever, right? So therefore, this will never allow a positive charge to move or negative charge to move towards positive charge. All right. So this is a small recapitulation of capacitor. Now what I'm going to do is I'm going to do effect of dielectric on capacitance. Effect of dielectric on capacitance. This is what we are going to do. So before I do an effect of dielectric on capacitors, so first what I'm going to do is without electric fields. First, without dielectrics. I just write without dielectric. Without dielectric means it is vacuums. It is vacuums. Alright, so the capacitors, the medium is going to be vacuum, right? There's no medium, so we will be having a vacuum, right? So without dielectric. So without dielectric, we say that electric field is going to be E naught. Alright, E naught is going to be sigma by epsilon naught. And epsilon naught is permittivity for free space or vacuum nature. This is for vacuum. Alright. Then potential is going to be, potential difference is going to be E naught D. And then capacitance is going to be Q divided by V naught. Alright, and V naught is going to be sigma by epsilon naught D, and this is going to be Q divided by epsilon naught A D. So finally what we get is C naught is going to be epsilon naught A by D. So this is the capacitance. This is the capacitance without applying, without inserting dielectrics, without dielectric. Right? This is without dielectric. So I'm going to write in a top without dielectric. So C naught, I'm going to write C naught, epsilon naught A by T. Epsilon naught A by T. Now what I'm going to do is I'm going to insert a dielectric. Alright. Now what I'm going to do is I'm going to insert a dielectric of the the size of dielectric is exactly equal to the size of the distance between two plates. So this is what I have. Now I'm going to insert a dielectric. Once I insert a dielectric, the size of dielectric is equal to the distance between two plates. So what is going to happen? We say a polarization is going to take place. Polarization is going to take place. All right. So because of polarizations, with dielectric, I just write here with dielectric inside capacitors. With dielectric inside capacitor, because of which polarization will take place. Polarization of dielectric will take place. Polarization of dielectric take place. Alright, due to which what I have is charge density would become now sigma divided by sigma p. And I say a sigma is a charge density without inserting dielectric. So I just say sigma is, this is the charge density without dielectric. And this is charge density due to polarizations. Charge density due to polarizations. Now I say, what about electric field inside? What about electric field inside capacitors? Electric field inside capacitor now would be equal to sigma minus sigma p divided by epsilon naught. Alright. Now electric field is going to reduce, right? So this is what I have. Now look at here. We are going to choose the linear dielectrics. So for linear dielectric, what happens is that for linear dielectric, this electric field is proportional to sigma. Alright, and this is again proportional to electric fields. Alright, therefore what we have is this is proportional to sigma p. Therefore finally what we get is sigma minus sigma p is equal to P divided by K, where K is dielectric constants. What is K? I say K is dielectric constants. K is a dielectric constant which has no unit. It is always more than 1. And for vacuum it is, for vacuum it is K is 1. If it is not vacuum, K is always more than 1. K is always more than 1. So this relation we found. Alright. Once we found these relations, now electric field is going to be sigma p divided by I'm sorry, this is going to be this. This is sigma. I'm sorry, this is not sigma p. Sigma is going to be sigma divided by K epsilon naught. Now this is electric field inside capacitors with dielectric. This is electric field inside capacitor with dielectric. Now we will find out the capacitance. This is electric field inside dielectric. Now what about potential now? Potential is going to be ED. So which is going to be sigma G divided by K epsilon naught. And what about sigma? Sigma is going to be Q divided by K epsilon naught A. Alright. Now I say capacitance, we define a capacitance. Capacitance is equal to Q divided by V. Alright. This is how we define capacitance. So therefore, C is going to be Q. What about V? V is equal to Q D divided by K epsilon naught A. These two cancel out. This goes up. Epsilon naught A divided by K. This is the capacitance, right? Look at here now. Right here without, with dielectric, this is going to be K epsilon naught A by T. So, effect of dielectric is here. That means, effect of dielectric is such that when I have a C, this is going to be, what about this? This is C naught. That means dielectric is going to increase. My capacitance is going to increase. C is equal to K times C naught. So this is the effect of dielectric is that when you put a dielectric inside a capacitors, and capacitance is going to increase by K times. Capacitance is going to increase by K times. Alright, capacitance is going to increase by K times. Now, what about I define here epsilon is equal to K epsilon naught, which is defined as permittivity of mediums and K is defined as epsilon divided by epsilon naught. K is defined as epsilon divided by epsilon naught. K is defined as epsilon divided by. So this is the defined. So dielectric constant is defined as the ratio of a permittivity in a medium to vacuums. The ratio of a permittivity of medium to vacuum is defined as permittivity, dielectric constants. Alright. Now here, look at here. Once you get this, then electric field would be equal to this, and potential is going to be this. I will discuss now later, right? These are the effect. These are the effect of dielectrics. When you put a dielectric inside a capacitance, capacitance is going to increase, then the permittivity is going to change, electric field is going to change, potential is going to change. So these are the effects of dielectric. Alright. These are the effects of dielectric. So now what I'm going to do here is now I'll explain you how electric field is going to decrease. So look at here. Once I put a dielectric, this is a dielectric. This is the induced electric fields, and look here. This is a positive negative charge surface density. This is a negative charge surface densities, and this is a positive charge surface densities. All right. So therefore, electric field, right? Electric field due to induced charge density is going to be in these directions, and actual electric field is going to be that directions. So therefore, electric field is going to reduce, but electric field inside capacitor is going to reduce. Alright? Why? Because this is going to cancel out by induced electric field, but not exactly going to cancel out, but it is going to reduce. Alright? So therefore electric field is going to reduce. If electric field is reduced, then potential is going to reduce. However, the charge remains same. Charge on the two plate remains same. Why? Because this is insulator, or this is dielectric, right? Charge on the two plate remains same. However, electric field is going to reduce and potential is going to reduce. Thus, capacitance is going to increase. Now let me define this: high capacitance and low capacitance. Low capacitance. All right. So capacitance is going to be a higher. All right. Capacitor is said to be a higher. The same charge is stored under a low potential difference, and this is what higher potential. I say higher capacitance. This can be defined like this. Same charge hold or stored under lower potential difference. This is a higher capacitance. What about capacitance is lower? Lesser, right? Same charge stored under higher potential difference. So this is how we define. Why? Because in any way the reason is this. All right. So this is what so therefore, since electric field is going to decrease and potential is going to decrease, a charge remains same on a two plate. Therefore, capacitance is going to increase. These are the examples, right? In circuit. Alright. Now what I am going to do is one very important, maybe in exam, what I am going to do is I insert a dielectric, I turn the capacitors and then disconnect it. A capacitor without battery, right? Disconnected, right? Inserting dielectric, let's say dielectric. This is what I have written is when battery is disconnected. Let's say when battery is disconnected. When a battery is disconnected. When a battery is disconnected, what is going to happen, right? When a battery is disconnected, what is going to happen, right? So this is what I am going to do, right? So when a battery is disconnected, look at here. I'll use here. What do you mean by battery is disconnected? I connect this battery, potential difference is V across this. So this potential difference V, charging of capacitor take place until potential is equal to V. So therefore this is going to be a positive charge. This is going to be a negative charge, and the potential difference is going to be V. This is how I say charging takes place. Now what I did is I removed this battery, disconnect the battery, and then what I did is I insert a dielectric. Then I insert a dielectric. Now when I insert a dielectric, so you will find a negative charge surface, you will find a positive charge surface, and you will be having an induced electric field. Induced electric field is in these directions, and external electric field is in these directions. Alright. So now electric field is going to decrease. You see, electric field is going to decrease. Alright. So in such a case, what about effect? Our main focus is effect. Effect is that capacitance is going to be this much. Why? Because potentials are decreased and electric fields are decreased. And what about electric field? Electric field is decreased. Electric field is going to reduce. And what about potential? Potential is also going to decrease. And what about dielectric permittivity? Permittivity is going to increase. And last, what about charge? Charge remains same. Why? Because charge remains same? Because there is no further charging take place. Why? We have already disconnected battery. We have already disconnected battery. This is the one case. Now next part is when battery is connected. When battery is connected. When battery is connected, then what I am going to get is this is what I have. When battery is connected, charging takes place, same procedure. Charging takes place until V become V. Alright. And then whatever it is, I am going to insert dielectric. Now battery is connected. As soon as I insert a dielectric, electric field is going to reduce inside. Electric field is going to reduce. Alright. Potential is going to reduce. Alright. Electric field is going to reduce and the potential is going to reduce. However, since the battery is connected, look at here, very important. However, since the battery is connected, in this case, since the battery is not connected, this remains as it is. Now, since here in this case, since the battery is connected, the potential, it lower the potential, it lower the electric fields. Now here we have a battery which fits up, right? Which gives off potentials, right? So this battery will maintain the potential difference. In a short, in a small sentence, I can say that this battery will maintain the potential. How this battery will maintain the potential? It supply extra charge. How battery maintains the potential difference across capacitor is supply extra charge. Supply extra charge until potential become equal to applied potential difference. Alright, so now charge doesn't remain charge doesn't remain the same, right? So therefore, in this case, capacitor is going to increase. Electric field remains same. Why? Because battery maintains the electric fields. And the potential remains same. Why? Because battery maintains the potentials. And what is going to change is now charge is going to change. Charge is going to change now. Now charge is going to change. Why? Because charge, a battery supply a charge, alright, so that potential remain same. So that electric field remains same. So this is very, very important, right? Then the permittivity again remains same. This is the point. Alright, this is the difference. So this is the difference between when battery is disconnected and when battery is connected. So this is the difference. Very, very important, right? So when battery is connected, then there is no difference in case of a potential difference and electric fields. What is going to change is the charge is going to change. Now charge is going to increase so that capacitance increased. Here in this case, charge remains same. How capacitance increase means you lower the potential difference. Once you lower the potential difference, then capacitance is going to increase. So this is the point. This is the point, right? So here I'll define one more. I'll define another definition of capacitance. I say the capacitor is higher capacitance, more charge, alright, stored under a given potential difference. Alright, more charge, stored under given potential difference. This is what we have. And this is the capacity is more. And less charge stored under given potential difference is less capacitance. More capacitance, less capacitance. We define the more capacitance, less capacitance in two ways. One in terms of a potential difference, another in terms of a charge. Alright. So with this, I'm going to finish today's topic. Now we are left with two small topics. Okay, so maybe next session I'm going to finish chapter number 2. Thank you.